Hello everyone, Mike with Spray Jones coming to you with another video, and we're going to be discussing retrofit spray foam for older homes that are made out of brick. I think this one is going to have a secondary part 2 video to it, in which we'll do old homes with the old shiplap and the old wood and the old wood siding products, cedar or what have you, because there's a lot of questions about building envelope and moisture entrapment, and do we vent and not, should we even do it, should we not, and the questions are good and the answer is really simple. Yes, we should be doing it, and we should be doing it with, you guessed it, closed cell spray foam insulation. So we're going to get into it, but before we do, thank you to everyone that is clicking on the likes and the subscribes, and to you that are sharing out comments. I really do appreciate it, and I like to hear and see the feedback. And the channel's growing, and the information is really having an impact on people's lives and their decisions, and that's good. We want to get truth out there, and we want to get facts out there, and we want to dispel all these myths and rumors and bold-faced lies. Okay, getting on to today's video. Should we be doing the spray foam to the brick? And the answer is absolutely you should. Now, I've got a lot of evidence to get through here, and I've got some commercial, we've got some really good residential. I'll try to tie it up as fast as we can and keep it all very relevant. This is a structure, a home that we did in 2006. So this was like year 2 of Spray Jones. This was my first truck and trailer setup. I built this spray rig in my yard, and this was getting going. And this gentleman, we actually had spray foamed the underside of the roof, non-vented. It was the first thing that we did for him, and he was so impressed with it that he wanted us to go back and spray the inside. So you can see that this building is 100% brick. I'm thinking that it was in the 1920s, or for early 1930s. So anywhere between 1925 to 1932 is when I was thinking that it was. This is what the interior looks like. So you would have a masonry wall that would be, I don't know, 1 or 2, I don't know how many courses of brick deep that it would be. It could just be the one course of brick. But what they did was they horizontally placed these timbers inside, rough cut timbers, that would be the vertical pieces that they could put to space the lath and plaster on. So I'll go to a close-up shot here so you can see what it looked like. Okay, here you go. You've got the back of the brick has been scratch coated on the inside to smooth it out. They've put these in with the mortar as they're putting the wall up, and then these 2x2s of rough cut fir are then wedged to be true, to be plumb. And then what they would have had is, you can see all the little nail holes here. They would have had lath. You can see where all the lath and plaster was. Plaster with the zebra striping going up. So the lath and plaster was removed, and this is the depth of what the wall cavity was. This building wouldn't have had electricity in the day that it was built. And so what it was done to retrofit it was a 2x4 stud wall, as you can see, was placed in front of it. Not all of this needs to be removed. Electrical wiring has been added, and then the closed cell spray foam is going to go into the wall, and it's going to go over all of these pieces. And that is really the beauty of the closed cell foam. And I've got 3 points of why I think it's obvious that this needs to be done. The first thing with closed cell foam that you do on a brick structure is that we stop the moisture drive and we control the air leakage, and that has got to be the most important thing. So building science wise, why do people get into confusion about whether or not these buildings should be insulated in the first place? Because they didn't have a vapor barrier or insulation to begin with. So all the air leakage and all the moisture could get out of the structure. It could wick and diffuse. It had air leakage and diffusion to get out and get gone. And there was so much heat loss, and these buildings were coal or wood fired to be warmed, that the buildings dried out very quickly on the inside, and there was nothing to hold and trap and contain the moisture up against the brick and therefore they could just lose heat rapidly, lose the moisture rapidly out of the brick, and there was no problem. Now when we go to retrofit it and we put fiberglass or mineral fiber up against it and a vapor barrier, all of a sudden now we've got this known amount of air leakage. I've shown you in the videos before. If you haven't seen them, click on them. I've got a video on vapor barriers and is spray foam a vapor barrier, and we go over air leakage, that 98% of the moisture in your wall is going to be air leakage. So if you go and put mineral fiber or cellulose or any of these things, you've put a poly vapor barrier on the inside, and then you riddle it full of holes when you go and put the sheetrock up, and you're going to have massive amount of air leakage, 400 and 600% air leakage as soon as the gyprock is installed. So that air carrying the moisture is going through the vapor barrier, through the bad insulation. Now the bad insulation or the cellulose or the mineral fiber or whatever is holding that water, holding that moisture, holding that damp air up against the interior side. And now you can play around with this freeze-thaw cycle. You can get frost developing on the inside, and then you can start to break and crack the mortar free, and you can break the bonds of the old materials free, and you start to rapidly degrade the structure when it's gone already 100 or 120 or 200 years and not had any destruction. All of a sudden you put this up and within 4 or 5 years you've destroyed it. That, building science wise, is what's going on. Okay, so how do we stop that? We stop that with air leakage. We control the air leakage, we control the perm rating, and we control it in such a way that we can provide an absolute. And I'm going to get into that. I'm going to get into a document that shows that we absolutely can. Okay, the second point of what we do is we fill the cracks and we fill the gaps and we fill all these little voids. When you go back to this wall assembly, look, how are you going to get around this furring strip? How are you going to get behind it? How are you going to fill all these little fissures? Let's go to another picture. There is a very good example of where things are cracking and breaking. And normally you would not want to get air leakage into here and moisture into here and frost into here, and then if that freezes, it's like a hydraulic jack and it just breaks it apart and splits it and makes it even wider. The spray closed cell foam is going to crawl in around all of this, and it's going to get into it and it's going to seal it. And then the third point of all of that is it's going to deal with all these irregularity cavities and seal them off. Seal them off from air and seal them off from moisture that's trying to make its way through. And it's going to bond everything together. I had a brick basement one time, and the bricks were loose, and the spray foam locked all of that in and stopped it from having all these problems. So this is the modern way that we want to deal with this structure. We want to come in, we want to build a 2x4 wall, like you're seeing here. 2x4 wall. We're going to put our modern electrical into it. This wall is set ahead of the old wall X amount of inches. Could be 1 inch, could be 2, could be 3. It doesn't really matter. We've got full depth of cavity here now where we can do 2, 3, 4 inches of closed cell, more than enough to retrofit the building and to build up the proper amount and get everything sealed. And we're not going to need to have caulking or a plastic vapor barrier, because we're going to have a continuous layer of the closed cell foam on the inside. And this is exactly why I think closed cell is the perfect product, because we're trying to control moisture. We don't want to let a product that the moisture is going to need a vapor barrier, plastic vapor barrier, and we don't want any moisture wicking through an open cell product at all. We want the bond of the closed cell, and we want the structural support that the closed cell is going to give. So old brick buildings should be done with a closed cell foam. And then here is an image. This is before we had switched and started using Wall-Tite. This is a Demilec product. Very good product, Demilec, and you're going to start to see us spraying a little bit more of the Demilec here in the future, just with what's going on in the industry. But not exactly our best spraying. I think I actually sprayed this. But we do have the requisite amount of thickness there to get everything sealed, and we have all the foam into this corner, which has been nicely opened up for us, so we can inject the foam right into there and get it filled up and sprayed, and you can see what it looks like when you're done. Here again, floor joist areas have been tied in around windows and what have you. All the framing that he's built out to handle where the drywall is going to go, the foam is just all behind all of these transitions and all the way up into these areas. And this building will go another 200, 300 years. Like the brick will start to destroy out of the outside long before any damage is going to happen from the interior side. Because this is all inert. This is all plastic. The wood can rot away. Things can move away, but the spray foam isn't going anywhere. And the fact that the lumber is all dry and it's not twisting and it's not continuing to move. We actually have more problem with new homes with the lumber twisting than we ever do with these old homes. These old homes have been so dry and so stabilized for so many decades that where they are at is where they are when we come in to do them. And again, you can see where all the lath and plaster was. But this is the only way to deal with these old retrofits, guys. Like, I just do not believe in trying to inject the foam into a hollow wall cavity, because you're not going to know where it's going to get. How are you going to inject into this space and then into here, but get it into here? It's just not practical, and you don't know what's going on, and you've got no depth to work with in the first place. So you open up the cavity like you saw, you build the stud wall, and then you put the spray foam in. Here's another place that we did. This is all brick and then old roof and cedar shakes, and this structure where we live was designated a heritage site, and so they couldn't change anything, and if they did, it had to be almost an identical match for what they had. So the brick in this situation is probably sitting around 80 years of age, and the guy bought this, and then he wanted to retrofit it and make it into his house. I think he ended up giving up on it. We ended up spray foaming it, but dealing with the Heritage Society, as most of you know, is a real pain in the keister. Here's just a quick image. This had lath and plaster going across it on the inside in front of the brick. This was retrofitted with 2 inches of closed cell wall tight on the walls, and I think we did 3 inches on the roof. Not the greatest looking picture here of the interior side for light, but you get the idea. Completely retrofitted with closed cell foam, heritage designation. And now I'm going to move on to 3 projects that we did that were old buildings that you can see. This building is called Canterbury. It used to be Roman Catholic Archdiocese owned it, and it again had the same heritage designation. It was in the same area that other home was done, but some developers bought this one and wanted to turn this into a mixed-use commercial building where they could have a cafe down below and they could have some trendy offices up top. I don't know all the things they wanted to do with it, but the big issue was we had 2 main stories, and then the 3rd story was up inside the roof. So the roof in this situation had to be spray foamed non-vented. It had no venting, and they didn't want to add venting. So we spray foamed it non-vented. We had to do all these dormers and all the little dormer roofs, and then we had to do all of the walls for each level, and we'll take a look at what the walls look like. Okay, here you go. Again, this is their masonry wall with some sort of hybridized coating, not coating, but a scratch coat of some sort, or how they formed this exactly, I'm not entirely sure, but the original 2x2 strapping was kept in place. Now, we had a meeting with them, and they did not want to go any deeper than this. So I think we had 2 1/2 inch was what we had to deal with. So we were shooting for a nominal 2 inches, which meant we'd be about a 1 3/4 inch low to a 2 1/4 inch to 2 1/2 inches high. Here we're spraying the wall tight. This was done in 2008. And so we had no choice but to go around and more or less overfill the cavities and then shave them down when we were done so that we could get just about the maximum in them. Okay, project number 2 is Dunning Place. This was sprayed in 2006, and this we're going to take a look at the engineering report. The next 2 will have some technical specs on them. This building, well, we'll see in the report. It's going back to 1900s, early 1900s. Masonry exterior. You're looking at the interior side, steel studded, retrofitted 3 inches closed cell. And the heritage architect in this situation gave a bit of a problem to general contractor and BASF and a number of people. So we're going to get in and read the report here in a second, but I just wanted to show you what this place looked like. Had a thermography scan done on this one, and it actually showed out very, very well, the thermal imaging camera, on how the 3 inches of spray foam performed versus other areas where it was a little bit thin. And you don't actually see quite as much as you'd think with the steel studs behind the sheetrock. This is a shot of in the basement. So they've brought all the walls out an inch, I think an inch or a little bit more. Yeah, it was more. And then they've done this Carlisle membrane on the inside around the windows. Windows were retrofitted, and the whole building from the interior side was retrofitted. But I really want you to see exactly what Morrison Hershfield had to say in regards to the objections that the heritage architect spoke on this project. So let's get into reading that report. Okay, here we have the comments that Morrison Hershfield had to respond, and let's just scroll down here because they get to the point here. June 2006, existing building constructed in 1914 uses brick masonry walls, terracotta trims, varying in thickness from 13 inches to 4 inches clay tile, so on and so forth, blah, blah, blah. Interior surface of the clay tile has a plaster finish. That's what we're seeing. The original building had no insulation. The second floor and part of the basement were insulated on the interior face 1983. Under current renovation plans, the entire building, with minor exceptions, is to be re-insulated using steel studs set 1 inch away from the interior face of the exterior walls and 3 inches of foam insulation. That's closed cell wall type. The provincial heritage architect has objected to our re-insulation plans and has argued that the only 1 inch of foam insulation should be used. His objections are based on 2 ideas: a belief the building has a thermal mass potential that will be lost if the insulation value is decreased, and a belief that the presence of interior insulation will reduce the potential for the masonry walls to dry towards the interior and thereby leave more potential for the exterior face of the wall to be wet at a time of fall freeze-up, resulting in frost damage to the brick on the interior face. It is our contention that both quoted beliefs result from a failure to understand either the building science principle behind the action or the impact of climate conditions in which this building exists. Boom! That is called a professional punch in the face. While the building definitely has thermal mass, it mitigates temperature swings during the summer months. It's totally ineffective during the winter months when energy costs are at the highest. Thermal mass is effective in providing some energy savings when the daily temperature swings both exceed and also fall below the interior room temperature to be maintained. The wider outdoor temperature swing, the larger the energy savings, where thermal mass is to be tapped. It is most effective if thermal mass is located adjacent to the interior space and not separated from it by insulation. American research results show that buildings with high thermal mass in a climate like Bakersfield, California, where cooling is the primary mode, may experience energy savings of up to 18%, whereas a similar building in Minneapolis, where heating is the primary mode, may not save no savings higher than 8% when the daily outdoor temperature is well below the room temperature. When the daily outdoor temperature is well below room temperature, which is the case in the largest part of Saskatchewan year-round, the thermal mass makes virtually no contribution. The conflict in this building is simply that the building is now uninsulated and the existing masonry walls provide very little insulating value. The building therefore loses a lot of energy in the form of heat. It is our contention that that insulating the building with 3 inches of foam insulation will offer far more in the way of energy conservation than would the minimal contribution on an annual basis of thermal mass contribution. Reducing the insulation thickness to 1 inch changes nothing, except the heat loss would be greater. The building is being renovated under the provincial CBIP grant, which calls for energy savings to be maximized. Unfortunately, the computer program used by CBIP energy loss calculations has no provisions to account for the impact of thermal mass. 2. One of the concerns related to insulating an exterior masonry building from the interior and adding a vapor barrier to stop moisture entering the exterior walls is that the balance of heat loss and gain and moisture loss and gain that has been established over the life of the building will be upset. The consequent results are largely unknown. There are, however, certain principles and environmental conditions that we do understand and therefore make some informed judgments. The prevention of heat loss from the building interior into the building shell due to interior insulation has been argued to reduce drying of the exterior walls because drying must now be totally toward the exterior. This may be true in very wet climates where wetting is frequent and outdoor humidities are high, resulting in poor drying conditions. In the prairies climate, this is not the case. Wetting is infrequent, although rainfalls may be intense when they occur. Sunshine during the summer months is also intense, and drying largely occurs towards the exterior. Folks, I've been saying it for a while. Sunlight is your number one way to dry up your roof and your exterior of your buildings. It is very unusual to have a wet brick face at freeze up. The concerns about frost damage to brick faces exists primarily where there are repeated wetting, freezing, thawing cycles. This condition is virtually unknown in Saskatchewan. The application of interior insulation is also accompanied by a vapor barrier which reduces the moisture loss from the room into the building shell. Most of our masonry buildings were constructed at a time when interior humidification was unknown and interior relative humidity, especially in winter, was very low. Mechanical humidification means there is now a much higher vapor pressure in buildings with a resulting larger moisture loss to the building shell. We really do not know what the impact of this is, although we do know that similar buildings also exist in climates where relative humidities are high all year round without apparent damage. However, because the application of insulation may result in the entire masonry wall thickness being at a lower temperature below freezing during the winter months, it would appear desirable to minimize the entrance of any moisture into the masonry wall from the interior. In this building, whether 3-inch or 1-inch of foam insulation is used, the vapor barrier which is provided by the foam will be in place. Closing out, whether a masonry wall is better served by being insulated along with a vapor barrier or by being uninsulated is not clear. However, in this building there is no evidence that the walls of the second floor have been damaged by having been insulated for the past 23 years. It therefore appears prudent to maximize the insulation on other floors as well in order to achieve maximum energy savings. Boom, folks, there you go. Go ahead and insulate. Now, I suppose if you do fit into some of the situations that this gentleman is discussing in freeze-thaw cycling, you can have a more extensive review of your building envelope. However, I still don't see how letting leaky fibrous materials into the structure is going to be better for your building envelope than if you go with airtight, watertight, spray foam insulation that is adhered. And that is probably the one of the most important things that we're going to look at in this last video and last dialogue here, where we get some technical dialogue going. Adhesion to the substrate in these old buildings is absolutely critical. Okay, so closing out here, we're going to take a look at this University of Saskatchewan change order. They queued up change order 17. They put this into the queue for a request for pricing, a description of change, revised wall type number 14, so off the drawings when they had already bid this. So the building and the structure, the construction was already ongoing. All right, we didn't have to bid this other than a change order. And they wanted to delete the fact they were going to use gypsum, wallboard, vapor barrier, girts, and semi-rigid mineral wool bat insulation type 2 and the airspace, and that's what they were going to be putting into these masonry walls. And then they wanted to revise it to keep the gypsum board 89 millimeter wood studs, so that's 3.5 inches, right, 2x4s, and then the 102 millimeters or 4 inches of closed cell spray foam insulation type 1. Basis of design is wall tight eco. This is old language here. Wall tight hasn't been called eco for quite some time, but wall tight into existing wall. And at the bottom, I like this. He says, demolition of interior walls revealed composition of existing exterior wall varied from design. So they're checking off the box, address an unknown condition. Now, I spoke with the architect because he had called me for a follow-up on this, and they were concerned about a couple of things. Air leakage to the outside and filling all of the irregularities in the actual wall assembly on how much space that they actually had. And so they switched it out to closed cell foam. And you've seen a lot of video of this where I've shown this in other videos where we've been spraying this wall assemblies and what have you. They stud framed it out, ran the wiring through conduit to all the different locations that they needed to be in, and then we went in and put the 100 millimeters of foam in, and then they heated and warmed each floor up because they were working from level to level. So we started on the 6th floor, worked down 5th, 4th, so on and so forth, until finally we got to the bottom. So each floor had X amount of thousands of square feet of outside wall that needed to be done. Total heritage building, total masonry on the outside, and a real legitimate concern that you need to get it right. And that's exactly why they switched it from mineral wool bad insulation and using vapor barrier and switching it to the closed cell foam. When I spoke to the architect, he had a few concerns with me about adhesion on the inside, and I said, no, the foam's going to stick just fine. It's going to get into all the mechanical little cracks and crevices and everything like that. I'm not worried one bit about getting good adhesion to the inside of the substrate. My number one concern is the fact that you're doing this in wintertime conditions, and it's a masonry wall, and I'm concerned about getting everything warmed up. Now, the general that had it did a very good job. They had huge indirect heating systems and ductwork to bring a lot of hot air onto each level. They got the surface of the concrete to warm up, and that's really important. If you're a spray foam guy or you're going to be receiving spray foam from somebody, you really should be getting the surface, the substrate temperature up as warm as possible. Get it into the 60s, I would say. Try and get it into 60 degrees Fahrenheit or 16, 15 degrees Celsius, and then your spray foam is going to go on at a better density. You're going to get much better yield, and you're going to get really good adhesion. Now, there are products that can go colder, but why push it? So this whole entire system showed them that they approved for the hospital and for a heritage building that they're going to get closed cell foam insulation in. And I think that we've stated and proven here, in whether you are having a house that was built in the 20s or the 30s, or whether you're working on a heritage property that's a municipal or provincial or state building, or you just got grandma's house in the inheritance and you want to retrofit it, closed cell foam is completely safe. It's the correct product that should be installed and get good bonded adhesion to the outside concrete and masonry wall, filling all the cracks, filling all the crevices, so that you don't have water and air leakage freezing into the assemblies. And if you do this, you're going to have a fine system. And I think the report that we just read from Morrison Hirschfield on the Dunning Place job ends the discussion. And this report here shows that they're addressing an unknown problem, and that the university wants to upgrade this to closed cell foam. Now, you tell me, would a university and a hospital take chances on a closed cell foam insulation for VOCs, adhesion, dimensional stability, all these kinds of things that we've addressed, fire, electrical wiring? No, it's got to pass everything. They have to have everything meet up with beyond just code. They have to meet that it's not going to cause them problems. In this situation, it was the exact right material that they needed to be installing, and they just need to get a good installer to come through and set it up and get it done, and that's what we did. So I hope that we've been able to prove the case to you here today for your project. Get somebody to consult with you on it, but I think the science is very clear that it doesn't need to be a problem with the closed cell foam. In fact, you're going to have a problem with the old-fashioned products and use the new. And the next video that I'll do up on something like this will be furthering along with wood and wood siding and wood studs, but I think you can take a pretty good guess right now as to how that's going to go. So thank you for staying this long in the video. Hit the like and the subscribe and the share. Share this with somebody that needs to see it, and we'll catch you on the next one.